choppy ending to that last clip. So apparently my video skills here are not very polished. So I just want to conclude with a brief example. And I guess before I do that, I'll just make a comment that when you do find a Taylor series from integration or differentiation, you should check explicitly the endpoints of the intervals that you get to verify the convergence of the Taylor series. And so for the one that we have here where we differentiated, this does converge for x from -1 to 1, not including the endpoints, and you could check that using just the consideration that at the endpoints, if you plug in x equals -1, you have a series whose terms do not approach 0, so therefore the partial sums, the sequence of partial sums cannot converge. And the same thing if you plug +1 in. And as I mentioned before, in the last video as we were working through the arctangent example, if in the series for arctangent you were to plug in either -1 or 1, you get an alternating series. And so because the size of the terms, if x is 1 or -1, are decreasing to 0, then in both of those cases, you have a convergent series. So that kind of illustrates some of the cautions maybe that you'd like to, that, you know, some of the things that you'll want to check if you're explicitly calculating an interval of convergence. Okay, I want to give one more. So there's only one thing that I want to do with this video aside from talking about checking endpoints for intervals of convergence, and that is to just caution that for all the examples we've seen, for all the examples so far, if the Taylor series converges, then it converges to the original function. So I'll say wherever the Taylor series converges, it converges this need not be the case. So we're going to look at the example that is the piecewise defined function. Okay, and it will be e to the -1 over x squared. And this will be if x is not equal to 0, and we'll define it to be 0 for x equal to 0. And it turns out that that this function has the Taylor series for this function centered at 0 is just is the 0 series. So this converges everywhere. So but it doesn't converge to 0 anywhere except at 0. I'm sorry, the Taylor series doesn't converge to 0. What I mean to say, the Taylor series doesn't converge to the function, to f anywhere but at x equals 0. So let me just show you a graph of this, and so that you can kind of see what's happening here. It is a strange example, but this motivates what the Lagrange error method that is described in your book, where you need to actually show that your Taylor series converges to the function that it approximates. So let's take a look here in Desmos, and I have gone ahead cooking show style and put in our function. I wasn't able to do a piecewise function here, and so I've gone ahead and just done e to the minus 1 over x squared, and then because of that I've had to put my base point just very, very close to 0. So this is more for illustration purposes, right? But you can see that as I'm increasing the degree, okay, now I run into some problems here past the 4th degree polynomial. You can see that that the function the Taylor series is the Taylor polynomials, pardon me, are the 0 polynomial everywhere. And so it's not actually what I've graphed here, but I was looking to try to graph something that that you could actually see in Desmos, and Desmos I don't believe will handle the piecewise function differentiation in a nice way. So what I want you to see here, though, is that the function in question, the blue function, is it's very, very flat. It's very close to 0, but not exactly equal to 0. And so you can, if we were to be able to zoom in enough, we would see that the red and the blue are not actually, right? So here, if we just continue zooming in, we see that these are close, but not exact, right? And so that's what's happening, is that we're seeing a function whose Taylor series doesn't equal the function anywhere except at the base point, even though the Taylor series converges everywhere. And that's a pretty strange example. So I just wanted you to have that picture in mind. This is also the subject of exercise 9 at the end of the section. I have not assigned that, but if you want to investigate it further, you can take a look at it. I thought that just the graphical description and the discussion here is sufficient for our purposes. So the assignment is to go through several of the problems in section 8.5. There's a lot here. And so please let me know, send me an email if you have questions. I'll be having office hours next week, and I can also meet with you at other times if those hours don't line up.